Okay, hi, this is Saka, and I'm here to try and help you with your 9.3 honors homework. So let's get going here. For number one, well, I'm gonna assume you know how to do number one. Remember the strongest forces in order are as H bonding, then dipole dipole, and then last one is London. So this one's the strongest, and then as we go down, this is the weakest. Okay, so hopefully that'll help you with number one. Number two, if it's polar, in terms of if we were going to go back and look at number one in terms of which one was polar and polar versus nonpolar. Um, this one, the London dispersion is nonpolar, polar, but also polar, whereas H bonding and dipole are polar only. This one and this one are polar. Okay. All right. Question. So this was one and two. So now moving on to question three. Water has an extremely high boiling point compared to other compounds because of, here we're looking for the intermolecular force for water, and I'll leave it at that. Number five, we're looking for hydrogen bonds. Remember, hydrogen bonds, you need to have H connected to O, H connected to N, or H connected to F only, okay? Otherwise, you don't get a big enough difference in electronegativity. Number five, if we're talking, sorry, number five. Oops, number five, again. So five, we're talking about strong intermolecular forces. Now, if you have strong forces, let's just summarize what you would have. You would have a high boiling point. You would have a high melting point. You would have a high viscosity. Remember, viscosity is resistance to flow. But you'd have a low vapor pressure. Remember, for boiling point, melting point, we're breaking apart the particles, so the stronger the intermolecular force, the more energy it takes to separate the individual molecules from each other. Viscosity is resistance to flow, so the greater the intermolecular force, the less it's gonna flow, and the more viscous it'll be. And for vapor pressure, the stronger the intermolecular force, the less likely it is to evaporate. Okay, and we'll talk more about that probably in class on Monday. So let's move on to number 6 here. Let me change my page. Number 6. Here we're looking at H, C, H, H, O with a dot, with a dot, with a dot, and another H. First of all, we know that CH bonds are nonpolar, so these CH bonds don't matter. But we know that there is going to be a difference in electronegativity between O and H. So H would end up being slightly positive, and the O part would be slightly negative. And this is because O is much more electronegative than the H is. Okay. So, all right, moving on to number 7. So for 7, we have water. Okay. And so you have to ask yourself what this is. So here we have oxygen with 2 dots, two unshared pairs, and you have H connected to it. So we know that this is a polar molecule, and the intermolecular force is probably what? It's going to be hydrogen bonding. But let's go back and look at the polar part. So this is a polar molecule because you have polar bonds and an uneven sharing of electrons. Okay. And then number 8, we have carbon dioxide. So it looks something like this. I'm not doing all the dots for the O. And even though we have polar bonds, this is a nonpolar molecule. Remember the two reasons. One, um, C has 0 lone pairs. And the second thing that's true is that C is surrounded. So R-O, I need to learn how to spell. Surrounded by O's. The fact that the O is the same thing, it's the same thing surrounding on all sides, makes it nonpolar. So because of this, because these two things are true, this is non-polar. Okay, moving on to number 9. New page. Number 9. So remember with number 9, oops, goodness, keep doing that. With number 9, remember CH bonds always nonpolar. And that should help you along with that one. For 10, um, goodness, for 10, you have the same thing, but one of the molecules, the molecule B is this one. C, CF, H, 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 H. And so the idea here is this one is going to have a polar bond because there's a difference in electronegativity between C and F. And then remember, if this is polar, the two intermolecular forces besides London for this one would be either H bonding, or the other possibility could be dipole-dipole. So clearly, remember, for hydrogen bonding to occur, you need a polar hydrogen, and none of these H's are connected to O, F, or N, so it can't be that one. Okay. 11. Okay, let me change the page here. For 11, you're looking for the greatest intermolecular force. So for 11, if you look at structure A is nonpolar. So the only forces acting are London dispersion forces. For structure B, you do have a little bit of polarity on the end with Cl. So it is slightly polar, and you're going to have dipole because of, if you have any force. C, because you have that OH, it's also polar, and because of the O is connected to an H, this is going to be H bonding. And then for structure D, it's going to be like B, where it's polar and dipole. So remember which one of those forces is the most, is the strongest one. Okay, 12 is referring to the same figure as before, but now it's asking you a different question. It's asking you which one of these, 3 of them are liquids, which one is a gas. So the liquids, if it's liquids, it has strong intermolecular forces because it's able to hold the molecules together strongly. The gas will have the weakest intermolecular force. And this is because if the intermolecular force is really weak, the molecules can't condense together to form a liquid. And you can use the stuff we did in 11 to help you answer that. 13. 13, they're asking you about hydrogen bonds. So remember, you're looking for H connected to O, H connected to F, or H connected to N. If it's not connected to any of those 3 things, then it's not hydrogen bonding. If they are connected like this, then it is hydrogen bonding. Okay, polarity. Which polar molecules? Remember, well, let's go through this one really quickly. New page. Then we need room for this one. So for 14, we have H, C, and dot, dot. So for this to be nonpolar, the carbon needs to have 0 lone pairs, which it does, but it's not surrounded by the same thing on both sides. Also, you have to wonder whether there's a big enough difference in electronegativity for this to be polar. So you'd have to look at the difference in electronegativity between C and N. Okay, and you have to see whether or not it would end up being polar or not. For H2S, it looks like this. So again, is the difference in electronegativity? Oops, forget the dots. Is that going to be between S and H? Is that going to be polar or not? For CO2, we've talked about CO2 a couple homeworks ago. We know that even though the CO bonds are polar, we know that this is a nonpolar molecule. And then for the last one, you have NF3, so this is N. And we did this one in class if you have me. And we've talked about how this one is polar because of that lone pair of electrons right there. Because of that, there's an unequal sharing of electrons that occurs. And you can kind of apply that to these over here as well. So anyway, good luck with your homework, and I hope this helped you.